Our next oscillator is compound pendulum. It is also a mechanical oscillator, that is compound pendulum. So, what is compound pendulum? It is any rigid body which can freely rotate in a vertical plane about an horizontal axis. So, this is any rigid body. It is an horizontal axis. Around this is a point of suspension. When we hold this object from S point like this, it will oscillate in a vertical plane. So, it will oscillate means this is the vertical axis, y axis, and let small torque is applied on it, and this body will reach at this point. Now, it is the center of mass of the body. When it is displaced by a small distance, then this center of mass will reach at this point. So, the distance between center of mass and the point of suspension is L. So, this is length of compound pendulum. So, first of all, we will define what is compound pendulum. So, it is any rigid body which can freely vibrate in a vertical plane, about a horizontal axis. So, it is basically compound pendulum. Now, first of all, we have to find the equation for this compound pendulum, and then we have to prove the motion of compound pendulum is harmonic, that is SHM, and secondly we have to find the time period of that harmonic oscillator. So, first of all, we will prove that the motion of this compound pendulum is harmonic motion. So, we can prove it by using mathematical equations. We know that there are two equations. First is deforming torque and second is restoring torque. Deforming torque, we know that deforming torque is I alpha, that is I means moment of inertia, alpha is angular acceleration. So, which may further be written as d square theta upon dt square. So, this is first equation, and in second case restoring torque. So, restoring torque in case of compound pendulum is its weight, because when this pendulum is lying at this position, its weight is mg, and if we resolve this weight in the components, then this angle is theta, this angle is also theta, and the two components of this mg, this weight mg force, because we know that weight is a force, these components are mg cos theta, because this mg makes an angle theta with this axis, it is cos theta, and the perpendicular axis is mg sin theta. So, this mg sin theta component will regain this pendulum to its original position, that is, it will move from this side to this side. So, this force, this component is responsible for restoring. So, restoring force means that is minus force into perpendicular distance. You know that the formula for torque is force into perpendicular distance, and minus sign is used for restoring because it pull back this oscillator to its original position. So what is force and what is this perpendicular distance? So you may resolve this mg as mg cos theta mg sin theta, or you may resolve this L as L cos theta and L sin theta. So this is force, this force may be written as minus mg sin theta into distance L. So it will become minus mg L into sin theta. So there are two equations, equation number 1 and it is equation number 2. So you can also resolve this perpendicular distance in sine and cosine, but I have resolved this force as sine and cosine function, sorry, sine and cosine components. Now the equation of motion from these two talk, you know that the equation is formed by deforming force torque is equal to restoring torque. Hence we will compare these two torque, that is comparing equation number 1 and equation number 2. We get I into d square theta upon dt square is equal to minus mgl into sin theta. Because it is deforming torque, it is restoring torque. Now finally we will compare this equation with the standard simple harmonic motion equation, that is d square theta upon dt square is equal to minus omega square x or omega square theta. You know that as theta is very small, we know that in case of pendulum, so it is a condition that this angle should be very small, means it vibrate with the small oscillations. So theta is very small, therefore sin theta approximately equal to theta. You know that when angle is small, then sin theta may be written as only theta. So this equation become I into d square theta upon dt square is equal to minus mgl into theta. So I have changed the sin theta as theta because this theta is required for standard equation. Now we can find this d square theta upon dt square is equal to minus mgl theta over I. Now put is all constants as omega square, because you know that this is standard SHM equation. Second derivative of theta, that is acceleration, angular acceleration, is equal to minus omega square into theta. So put this mgl over I as omega square, this one. So this equation become d square theta is equal to minus omega square theta. So this is standard simple harmonic motion equation, where omega square is this. So this equation proves that the motion of this compound pendulum is harmonic. So first part is proved, that is the motion is harmonic. The second part is we have to find the time period of this oscillation. So what is time period? You know that time period can be calculated by this omega square value. So since omega square is equal to minus mgl upon I, and omega is mgl over I under root, and omega is, it is 2 pi by t, it will become mgl over I under root. And finally we can find t from this equation, and this is required equation for time period. So what is t? This t will be 2 pi into under root of this I over mg into L. So this is the time period of oscillation in case of compound pendulum. Now T is equal to 2 pi into I. I means moment of inertia. M mass of pendulum. G acceleration due to gravity. L is the length, equivalent length, that is distance between S and C, point of suspension to the center of mass. Now we will discuss this time period in detail. So discussion on this time period. So we will discuss this formula in detail. So there are 2 or 3 corollaries we can derive from this time period. So first of all, we have to find the value of I. What is I? It is moment of inertia. So I am using the theorem of parallel axis. In case of compound pendulum, this I is equal to IAC plus ML square. This is L means this one, L, and IC means the moment of inertia about center of mass. So when this axis will pass through this center of mass, then what will be the inertia of this body? The inertia of this body about the center of mass is IC, and plus the distance between these 2 points. So this is the value for moment of inertia by using the theorem of parallel axis. So this formula is obtained from theorem of parallel axis for moment of inertia. So you have read this theorem in 10 plus 1 class in the case of, in the chapter of rotational motion. So this I C may further written as M into K square. So what is this K? Its K is radius of gyration. You know that K is radius of gyration. This K. So this I is the sum of mk square plus ml square. So you have to put this value I in this equation, and you will find the another formula for time period. So this T become 2 pi into m k square plus m l square over mgl, or on solving we will take common this m from here numerator, and this m will cancel with the m, and the final answer is k square plus l square over gl, or it is 2 pi under root of this k square by l. So I am separating this k and l, k square by l plus l square by l, that is l, over g. So I have rewritten this equation like this. So I am dividing this l, this term by l, the two terms. This is k square by l plus l square by l, that is l, over g. So basically I am doing this only to compare this time period formula with the standard formula. You know that the time period formula T for simple oscillator or simple pendulum is 2 pi under root L over G. This answer. So I am comparing this formula with this formula. That is, it is G here, 2 pi is 2 pi here, and root, and this one is L. So this formula is T is equal to 2 pi L over G. So I have put this value k square by L plus L as capital L. Capital L. So what is this capital L? So it is equivalent simple pendulum length, or length of equivalent simple pendulum. So it is L is length of equivalent simple pendulum. What is equivalent? Means if we consider this compound pendulum as simple pendulum, then the length of this pendulum is this. It is L plus k square by L. So in case of the proof of this compound pendulum, we have taken only SC, that is L, as a length, but from this formula it is clear that it is not L. So we will consider the equivalent length, if we draw this equivalent length in this case, then it is point of suspension S, it is center of mass C, and it is L. We know that, small l. But from the formula it is clear that there is addition of this term in L. So this extra term, that this point is O point. The CO is K square by L. So this is additional distance. So the length, total length, is counted as the equivalent length of compound pendulum. So the formula is time period 2 pi over K square by L plus L over G, or this is L, capital L, the formula. And this length is shown here in this diagram. So if we consider this whole pendulum as simple pendulum, then this is the length of simple pendulum from S to O. It is not S to C, it is S to O. So there is another property for simple compound pendulum, is that interchangeability. So what is interchangeability? From its dictionary meaning, interchange. If we interchange the position of this compound pendulum in reverse direction, that is, this O point is lying here, this point O point is here, it is inverted, and S point is here, this point O, and C point is here. So this one is O, C and S, O, C and S. If it is inverted, it's called interchangeability. So it means when we vibrate this compound pendulum like this from this side, it will vibrate like this, and if we interchange then like this, it will oscillate like this. So in both cases, the time period remains same. The time period remains same. There is no any difference in the time period. Either it is suspended from this side or suspended from this side. So this is called interchangeability. So that is, this T is taken as 2 pi under root this K square over L dash plus L dash. I have replaced L as L dash. Then the answer remains same. So on interchanging the position of the pendulum, there is no change in time period. That is time period T dash. So we can say that this T is equal to T dash, means formula is correct in both cases, either direct or inverted. Now, next we will find the condition for time period to be maximum or minimum. Condition for time period to be maximum or minimum. In what case the time period is maximum, and in what case the time period is minimum. So you know that in mathematics we have already studied the functions for maxima and minima. So I am applying the same formula or same condition of maxima or minima here for time period. As you know, if there is function y, its value is maxima or minima, so you can take its double derivative. So on taking double derivative, we can find maxima or minima of any equation, or either using double derivative or using single derivative. So you can find by using single derivative also. So dt, we know that we have formula T is under root 2 pi K square by L plus L over G. So taking derivative of this equation on both sides with respect to L, because it is equation in T and L. T and L are function variables and others are constant. So we will find the derivative of this equation, and finally put that derivative is equal to 0 for maximum or minimum. So, you will find that this L is plus minus k. So, you may solve this equation by yourself. You will take only derivative of this equation with respect to L, and finally put that L is 0, and you will finally got the answer L is equal to plus minus k. So, these are the this is the condition for time period to be maximum or minimum. So, this is all about this compound pendulum. So, in next lecture we will find the torsional pendulum. Thank you very much.